I welcome you all to this Spark Research YouTube channel. This is Veer, and here we are going to take the contents from this analog and digital communication. And in this session, we are going to discuss about this passband transmission system. So this is the second and the concluding parts. And in this session, we will focus on these topics: the probability of error for BPFSK, BFSK, then BPSK, QPSK, and M-ary PSK, FSK, and QAM. All these things, right? So all these are what, like, modulation technique, which is being used in the passband digital communication system. So the challenge is the probability of error. So we have to find out, right? So we'll talk about it. Here is the syllabus for your fourth unit. If you look into that, we have already discussed the passband communication system. Now we will look into that, how to find the probability of error. So in this session, BFSK, you know, the binary phase shift keying, binary phase shift keying, binary frequency shift keying, quadrature phase shift keying, and M-ary. So multiple signals are there, right? FSK, so frequency shift keying, and the QM quadrature amplitude modulation. So we'll look into all this. Okay, so let's go ahead. Okay, so question number one is, suppose whenever we are, like, why the probability of error occurs in any type of signals. So the major problem is that whenever we are sending, suppose transmitting the bit 0, right, and transmitting the bit 1, but there is a interference in between transmitting bit 1 and 0. Means if we will look into this region, in this region, see here, then what is the problem is that in this region, like, you have sent the data bit till here 0, but in this region, what is happening in this region, you are going to detect the 1. Means definitely probability is low, but there is a chances that you will get the data 1 even if you have sent the what, bit 0. So this reason, the may sometime will detect the 1 instead of 0. Similarly, in this region, what will happen, sometime the data may be detected 1, but you have transmitted what, 1, right? If you can detect the 0. So that is the problem. Means if you are transmitting 0 and detecting 1, that means you are detecting the wrong information. Again, if you are transmitting the 1 and if you are detecting the 0, means here, then again you are detecting the wrong information. So what is the chances that whatever the signal you are detecting, that may be the wrong information? So that is called the probability of error. So that we have to find, right? So here's the conditional probability. So probability of error is equal to P of your bit 1 chosen, and condition is that bit 0 was sent, right? So this is the probability of error, plus for this one you have sent the bit 1 and detecting the 0. So add both of them and then you will get the probability of error, right? So this is the basic concept. Now actually we have the two types of the detection system also. First is your coherent. So coherent detection is a method where the receiver uses a locally generated carrier signals that is synchronized in the frequency, right? Frequency and phase. So this is the major crux of the the coherent, that it will synchronize in frequency and phase. But in non-coherent detection method does not require any synchronization, not requires any type of the, independently you can detect, right? But and so if you are detecting independently, no need to synchronize. So of course this detection non-coherent will be very easy. But the again, after detecting, you have to arrange all those information, so that will be the difficult. But in coherent detection, your circuit may be the complex, because you have to synchronize the frequency and phase, but it will be the, the better solutions, because no need to add all those the informations that you have detected. So we will actually look it, primarily we will focus into this coherent detection. We will but we will also go through the quickly through the non-coherent detection either, right? So let's just start. So coherent detection, first here, RF pulse PT is given. PT is the you are transmitted. the pulse train which is being used as a carrier, p dash t cos omega ct. Cos omega ct is nothing, your uh, carrier frequency. So for filter matched, your RF pulse PT followed a sampler in this. So rho square, that is the signal to noise ratio, that is equal to the SNR equal to twice of EP divided by N, and EP is the energy of your PT. Clear? So how will you detect? So your PT is going there, and then the transfer function, and then decision, the sample and hold, and then threshold devices that will make the decision. So likewise you can get the proper information, and so that is how you will detect, right, the information. Similarly here carrier frequency is there, and with the help of the carrier frequency you can multiply with the pulse train, and then you can pass it through the device ht, that is the transfer function, your p of tb minus t. And then why are we using this pulse train? Because to modulate and also simple and hold techniques. So pulse train have the some particular tb band, tb bit, the timing, and the threshold devices that will make a decision, right? So this is a simple technique to use a coherent detection. So now let's see the the general probability of error. First we will look into the general probability of error, then we will look at the special BPSK and all those. So here FSK is there, general one. So here for we are talking about the polar signaling here. So FSK, suppose frequency shift keying bit 0 1 are transmitted by RF and having these like F1 is this one. So you can check it here. This is your suppose uh, q2 qt and pt. So qt is suppose for bit 1, and for pt is for bit 0. So two different bits we are transmitting. So you can check it here, it have the two different frequencies, right? So we are omega c minus of del omega by 2, and here we are also using the del omega by 2 pt, right? So here actually whenever we are using the pulse train, that is rf, here in you can check it here, the pulse train omega c minus del omega by 2. So one of them should be plus, so let me make it plus, right? And another del square root 2 cos of omega c plus of del omega by 2. So from here only you can make. So p and t, right, 1 and 0 bit are there, and now we have to find out the error, right? So to compute the pb, that is the probability of error in bit, we will use the equation how. So epq we will find, right? So that will be 0 to tb, that is and pt into qt and dt. So put the values of pt from here, and qt from here, and then integrate it. So this will be the epq. So that one error one, right? So error means the in between 1 and 0. So that one we will find out, and then after putting all these values you can get the the a into a square, and a square root 2 into a square root 2. So 2a square, take it out, and then integrate it over 0 to t, right? And after integrating, what will happen? You will get these term cos, and then independently you can integrate. So this will be, you will get the same type of the function, and in another term like here also you will get, right? So here you will get the higher term. So cos c into cos t, you can get like cos c plus t divided by 2 plus cos c minus t divided by 2. With the help of that equation you can solve, you can get the value of epq. Once you will get the epq value, so further in order to minimize the pb, that is probability of error, epq must be minimized from here, and epq should be how much? Minus 0.217 a square tb. That occurs only if tb is equal to how much? 1.43 pi. So this is the condition only for EPQs to minimize. So del f, in that case del f will be 0.755 divided by TB. So after getting these values, the probability of error, how to find q function, that is q function is nothing, 1 by twice by square root exponential function of minus u square by 2 du, right? You should remember that thing. So we are shortcut we are writing pb is equal to q square root of snr, that snr max, right? So here already we got these values. So 1.217 square TB. You can just as whatever and the noise is noise. So here we are getting the signal power. So signal power will get the difference of your the power that contains in the masses and minus of your power that you contain in the noise. So just will take the difference, you will get this one, right? So you can in this way you can get the probability of error in the FSK. So this is general one, and especially we will look into the BFSK. So this is not for the BFSK, so we look into them. Okay. Similarly, for ASK, you can get the probability of error that is equal to Q function EB by N, and Q function is nothing, already I told you, so you can check that. And for phase shift keying, also you can get the probability of error like square root of 2 EB by N, right? Okay, so now we will find especially for each of one. So waveforms error, what is that exactly error? Already we have discussed. So in signal, the space diagram, you can check even if the amplitude will vary from the large amplitude, no problem because the space gap is large, right? So this is the in the space diagram. So you can check it here. That is why we are using like D. Also you can find out that is the minimum space, the gap to find out the probability of error. So that will helpful, right? Okay, so let's start to find the probability of error for one of the all the points here. One, so let's start from the BPSK. So first is your binary phase shift keying, right? So we are going to start it now. Okay, so how we'll find out? So in binary PSK system, the pair of signals x1 and s2t represents your like this. So s1t binary phase shifting. So it have the two different phase, right? So here see s1 is equal to, we can write square root of tb by tb. So this one belongs to the one signal s1t, and if we'll shift plus pi, of course it will become the s2t. So plus pi means cos, then it will minus cos. So your 1 and 0 signal, you can say like that. Okay. So in the signal space graph, you can represent. So here you can calculate the energy for both of them. So minus of EB for one information, 0 information or 1, like, and a plus of EB. So likewise you can check it here. Here the phase is there because of that. So information you can see here for one, it is starting from here one, the one position, and for another, like another signal, suppose 0, you are starting from the phase shift by pi. So this is the difference here. You can observe the difference in between the two graph. So one is being used to transmit 1, and another is being used to transmit the 0. So here is the major points, and corresponding to these you have the equation. So right, so just add the pi at the pi angle, that is the phase shift keying, right? And here is the signal constellation graph, right? So in the graph you can show the phase difference of pi. So the angle here now, so this angle is how much? This angle here, angle we are showing, that is the pi, right? So this is the pi angle. Okay. So signal space diagram for binary PSK. From this pair of the equation, it is clear the case of the binary PSK, there is no function of the unit energy. So phi 12 you can write, because in order to solve it quickly you can write. So you can rewrite S1t is equal to a square root of EB and phi 1t, right? Why are we writing it? So that it will be easy. So EB is there, and the remaining parts you can write phi 1t. So s1 s2t also you can write, and then we will find out the s11, that is the s11 s221, right? So s1 into phi 1t and then dt, if you integrate it you will get this eb, and similarly for another signal you will get the minus of eb. So that is why we have already represented it like in the signal space diagram. Okay, so now we will find out the probability of error. So how we'll find out the probability of error in binary PSK? So here x1 is related to the received signal st. So x1, again we are going to integrate it over 0 to tb xt and phi 1 t. So put the values here now. The as per the conditional probability and exponential x1 minus x21 and whole square. And further, if you'll solve it and then you can replace using the q functions, you will get the p10, that is probability of 1 and 0, this function. And further, replace this exponential function, like we will try to replace using the q function. So you can equivalently you can write 2eb by n naught. So finally the probability of error will come q of square root of eb by n naught. This is valid for coherent detection. So coherent detection and BPSK, right? So okay. Similarly, we will find out for the another one. Now QPSK. So QPSK means now we'll have the four different phase, that is called quadri-phase phase shift keying, right? So here like not only quadri-phase, so we can also make it the 16, 32 or 64 bits. It's depending on the bits that how many we are using. So in order to achieve this quadri-phase, we have to use the four bits. So that angle may be the pi by 4, 3 pi by 4, that is 90, and 180 plus 45, that is 235, likewise, right? So here is the signal, and the signals can be rewritten like pi 1. Again we are trying to write in a smaller way. So pi 1 we can suppose, and phi 2 also we can suppose, so that like if we have the four signals. Now here we are going to use the like different angles, so pi by 4, then again 3 pi by 4, 5 pi by 4, and 7 pi by 4. So these are the angles we are going to use here in signal space diagram, right? So here you can see this is the 45, 180 plus that 45 to then 180 minus 45, the 90 plus 40. This is 180 plus 45, this is 270 plus 45, right? So now here you can see the phase is the changing. It have the four phases, so that is why this is called the quadri-phase, that is four phase, right? And of course these the will have the patterns of 0 0 0 1 0, and 2 bits. So here we are using 1 1, here we are using 0 1, and this is your 0 0 and 1 0. So we have the 2 bits of patterns, okay? Corresponding to all these you can get the values here. So you can, how will you get? So put the values in this equation for 1 1 and 1 0, all angle, just put the values, and you will get the S1 value and S2 value. So what will be the S1 signal, and what will be the signal S2 for all these signal constellation graph? Here the signal space graph is there, so you can get like, so all these are the the S1 power and S2 power, right? Okay, so now we'll find out the probability of error. So S2 xt, you can write signal and plus the noise. So WT, additive white Gaussian noise, right? So and so again we'll integrate it over xt to 5xt into 51t. 51 already you remember what is there, and then put the values here, and you will get the integration this one, right, for x1. Similarly for x2, again you will get the same value, just like that, square root of e by 2 and w by 2. Why is this e by 2 we are achieving? Because this time we'll have the half of power, right? So the average probability of a correct detection is the 1 minus and p dash and whole square. So now if we'll put p dash is equal to like your q of a square root of e by p, then you will get a minus b whole square, like 1 minus the a square minus 2ab plus b square. So since this will contain the higher the terms, so we can neglect it. So directly you can get the second term. Here the average probability modulation symbol for QPSK is therefore like P is equal to 1 minus PC, and 1 is there now. So 1 means the complete information. So error only we want to detect, right? So that is the carrier, the correct probability of error. So directly we will detect the probability of error only. So one we can remove, and we can consider these things, and higher term we can remove, so we'll get this probability of error, that is twice of q of e by n naught. So again, now the in the QPSK signal we note that since there are two bits per symbol, not only one bit, so the signal transmitted signal energy per symbol is twice the energy per bit. So that is why E is equal to twice of EB. So further replace it, P is equal to twice of Q square root of 2EB by N naught. So the minimum probability BER is equal to the Q of 2EB by N naught, right? Okay, so similarly, we can continue to talk about the M-ary PSK. So M-ary means the numbers of the, the signals will be the higher. So M means the, suppose it may be the, like we have discussed 4. Similarly, it may be 8, 16, and 32, like that. So again, the angle will be smaller and smaller if we are increasing the M. So the problem is that if we'll keep on increasing the numbers of the bits, of course, what will happen? The angle will keep on decreasing, and if angle is keep on decreasing, then of course the probability of error will be high and high. So here, the let's take it quickly. So how we'll find out that the signal space, like this is the D, that is one of the term we are going to introduce, because the D will tell you that whether it will have the probability of error is higher or lesser. Means if D is high, means of course probability of error is less. Both are reverse proportional, because the gap, right? D is nothing, the gap in between the two bits, right? So for 4 bits, like 2 bits, we have seen that the gap, the angle gap was 90. For 8 bits, now angle gap will be only 45. So that is why this one is important here. So M is the number of bits that we are using. Suppose for the case of M is equal to 8, your again you can find out the probability of error for M-ary. So that will be twice of divided by n naught into sine of pi by m. Okay, so for similarly for M-ary QAM, so here in M-ary QAM, M-ary PSK, the in phase the quadrature components and modulated signals are interrelated in such a way that envelope is constant to remain the constant, right? So the QAM is hybrid modulation. In phase the carrier experience amplitude as well as the phase modulation. That is why this is called QAM. So this is nothing, the combination of amplitude and phase. So M-ary PM you can design here. You can check D mean equal to 2 into a square root of a naught. D mean is nothing. You denote the maximum distance between the constellation signal, right? Signals present in the constellation. And of course, it should be high, but we cannot keep it high because we are trying to increase the transmission rate. So find out the S1 and the signals, and then you can find out the signal constellation for M-ary QAM, right? This will have the higher constellation, and probability of error will be probability PC is the nothing, that is your the correct detection for M-ary, and probability of error is the 1 minus of P of C, right? PC is equal to 1 minus P of E. So here again you can use L is equal to a square root of M, and you can put the you can use the formula that we have already used in the QM, and just put the values of the probability of error, that is P of E, so that here it will be twice of P of E. If we'll solve it, then you can put the values here in the probability of error that we have already solved, and you will get that probability of error, right? So you can check it how to find out the details. Now we are running, the time is very short, so let's go ahead quickly. Similarly, frequency shift keying, also you can check the two different signals are there, and so power again, again we can calculate the SI, and for different frequency value signal constellation graph you can check. For BFSK, again the two graphs are there, and the signals you can check, the F1 and F2 are there. Probability of error you can calculate, again x1 and phi1t. So here either you can EY of one expectation you can calculate using the conditional probability, that will be equal to EB, right? And further if you will calculate that probability of error, you will get the Q of EB by N naught. You can check that how to find that, we have already discussed in the BPSK, so the same process we are going to use it here. Okay, so here is the final probability of error for B FSK binary. Similarly, for non-coherent, whatever we have discussed, that all belongs to the coherent type of the signals. Here it is for non-coherent. Non-coherent you can ignore because this may not be in syllabus, but I think this is very important part. So sometimes question may also come. And so envelope detectors we are going to use in the non-coherent techniques. So let's go quickly. So amplitude shift keying, here is the probability of error. You can check it for coherent detection. Here's in graphs you can check. For coherent detection, of course, the probability of error is less. For non-coherent, it is little bit higher, right? Similarly, for PSK, differentially PSK, you can check here. For coherent, the probability of error is less. Non-coherent, it is higher. And probability of error, you can find, this one equation is here, right? How to find. So phase shift keying, that is frequency shift keying, and so again probability of error, you can find out all these are related to the non-coherent only, right? So for M-ary also you can check the probability of error, you can find this one equation, and for M is equal to 16, of course probability of error will be very high. As you will increase the value of M, probability of error will be high, high and okay. So QAM also the signal constellation you can draw, and the probability of error will be this for non-coherent, right? Okay, so that's all in this session. Thank you to join, and if you need more details about the non-coherent detection, you may drop the comments in the section comment sections. Will especially will come with another session for non-coherent if it is required. So thank you to join.